Hello, and in this video I'm going to introduce the concept of complex power. This is the fourth use of complex numbers that we've come across in this module so far. A quick reminder of the other three. The first one was phasors, using complex numbers to represent oscillations. The second was complex impedance, using a complex number to represent the ratio of the phasor representing the voltage across a component to the phasor representing the current flowing through the component. And the third one that we just mentioned in passing was this idea of complex oscillations, using a complex number to represent an oscillation which, as well as having a period, can also grow or shrink with time. But we can also use complex numbers in a very useful way to represent the power in reactive networks. The first thing to think about is what would we want a complex representation of power to actually do? And one useful answer to that question, which turns out to be particularly simple to derive, is to have a real component of the complex power representing the average power dissipated by the component, the average power lost to the circuit. And then the imaginary part of the complex power would tell you the maximum rate at which energy is stored or released from the electric and magnetic fields in the reactive elements of the component. Now, what do we know so far about both of these quantities? Well, we've already derived the result that the average power dissipated in any network with an impedance of R plus Jx is given by the square of the amplitude of the current divided by 2 times the real part of the complex impedance of this network. I've just called that R here. We also know that the maximum rate at which energy is being stored or released from the reactive elements in the components is the current flowing through the component times the voltage across the reactive element of the component. Vox here is the voltage across the imaginary part here, again divided by 2. I need to think about this second term here in a bit more detail. If I represent the voltage across the imaginary part of this impedance here in phasor terms, I might call that Vx phasor. I know that's equal to the phasor representation of the current flowing through this network multiplied by the complex impedance of this imaginary part. So that would just be Jx in this case. And if I take the magnitudes of this, the magnitude of the voltage phasor will be the magnitude of the current phasor times the magnitude of Jx. Well, the magnitude of Jx will just be equal to x. By definition, x is a real number. The total impedance is R plus Jx. The magnitude of the current phasor is just equal to I0, the amplitude of the current. The amplitude of the voltage phasor is just going to be equal to Vox, the amplitude of the voltage across the imaginary part of the impedance, x. So this gives me this formula here. I can substitute in for Vox into this formula here and get that the maximum power, that's the maximum instantaneous power being absorbed or returned to the circuit by this component, will be I0 times Vox, which is I0 times x divided by 2, or I0 squared times x over 2. Except that I have to put a plus or minus in there. And the reason I have to put a plus or minus in there is because x can be negative. In fact, if this was a capacitive component, a capacitor has a complex impedance of 1 over j omega c, or minus j over omega c. It has a negative imaginary part. So, it's quite possible that x will be negative. But the maximum power, that's always got to be a positive number. So I'm just going to take plus or minus this to cover the fact that even when x is a negative number, I want a positive number out of here. An alternate and perhaps simpler way to write that is the maximum rate of energy being stored or released back into the circuit is I0 squared over 2 times the modulus of x. Right, so I've now got an expression for the average power dissipated and the maximum rate of energy stored, and you'll see that they look very similar. In fact, consider what would happen if I had some quantity S, which I'll call the complex power, and I defined it as being the square of the amplitude of the current divided by 2 times R plus Jx. In other words, I0 squared over 2 times Z, where Z is the complex impedance. The real part of this is going to be I0 squared over 2R, and that is equal to the average power being dissipated. The imaginary part of S is equal to I0 squared x over 2. And if I take the modulus of that, that will give me the maximum rate at which energy is being stored or released back into the network, which is exactly what I wanted from my definition of complex power. And this is a very simple way to calculate it. You take the amplitude of the current flowing through your component, square it, divide by 2, and multiply by the complex impedance of your component. As with any complex number, you can plot it on the Argand diagram. And if you do that with complex power, you'll end up with a complex power that may be somewhere around about there. There are particular names that we give to the real component of the complex power. We call that the active power. And that is the average power being lost to the circuit. And the imaginary part, we call that the reactive power. And that's the maximum rate at which energy is absorbed or pushed back into the circuit from the electric and magnetic fields in the capacitor and inductor, respectively. It's equally possible to derive the complex power from the phasor representations of the voltages and the currents. And the way you do that is you take the voltage phasor, the phasor representing the voltage across your component, multiply that by the complex conjugate of the phasor representing the current through the component, and dividing that product by 2. Why take the complex conjugate? Well, that's not immediately obvious, but it is essential to do. I'll try and explain why. We'll start off from the complex impedance of our component. Z has a real part R and an imaginary part X. And I can write that in polar notation as the magnitude of my complex impedance, modulus of Z, and a phase term theta, the phase of the complex impedance. Now, if I want to know the phasor representing the voltage across this component, I would take my complex impedance and I would multiply it by the phasor representing the current flowing through the component, which I've defined here as I0 exp j phi. It has an amplitude of I0 and a phase of phi. Right. That gives me a voltage phasor, which is given by the current amplitude times the complex impedance Z multiplied by e to the power of j theta plus phi. Now, if I just multiplied that voltage phasor by my current phasor, I would end up with this. That's not what I want. What I want for my complex power is the magnitude of the current squared divided by 2 times the complex impedance Z. And I've got this extra term e to the 2j theta in here, which is going to be difficult to get rid of. However, if I multiply the voltage phasor by the complex conjugate of the current phasor, that would give me I0 times Z e to the j theta e to the j phi times I0 e to the minus j phi. Sorry, that should have been a phi. Because that is the complex conjugate of my current phasor. Well, that term cancels out with that term. That's just going to give me I0 squared times the modulus of Z times e to the j theta, which is I0 squared times Z. And if I just divide that by 2, I will get the complex power that I wanted. So to get the complex power, I have to take the voltage phasor multiplied by the complex conjugate of the current phasor and divide by 2. Before I leave this one, I'll just mention a couple of derived formulas that we can make. Because we know that the complex power is the voltage phasor times the complex conjugate of the current phasor divided by 2, and the voltage phasor is the current phasor times the complex impedance, we can derive these two formulas as well. The complex power is the square of the amplitude of the current divided by 2 times Z0. It's also the square of the amplitude of the voltage divided by 2 times the complex conjugate of the complex impedance. And finally, before we go and do some examples which might make this a little bit clearer, I should just mention that there are some special units that are used when talking about AC power. The active power, that's the power that's actually lost to heat, actually leaves the circuit, is expressed in watts. The complex power tends to be expressed in units called VA, or volt amps. It's got the same kind of units as watts, but we don't refer to it as a quantity in watts, just so that it's clear that we're talking about a complex power rather than an actual real amount of energy that's leaving the circuit. And the reactive power, we use units of VAR, volts amps reactive, just to emphasize again that this is not a real amount of power leaving the circuit. This is energy that is stored and then released back into the circuit sometime later. That's a bit of a complex topic. Hopefully the next video, when we do some examples using complex power, will make it a bit clearer.